Hello everybody, my name is Kyriakos Vamvoudakis. I'm a professor at Georgia Tech, and this is a presentation on the MathWorks tutorial. So first, I would like to thank Anastasia and Roberto for this wonderful invitation. I would like to thank my colleagues who presented before me, and this talk will be on using reinforcement learning to solve control problems for robotics. So let me give you the outline of my talk. So my talk will first describe what is an optimal control problem and why reinforcement learning can be used to solve such problems. The simplest state that we can talk about when we talk about optimal control are solving optimal control problems for Markov decision processes. Then I will show policy iteration and value iteration to solve the Markov decision processes. And these are the basis for reinforcement learning to solve such processes. Again, policy iteration and value iteration are iterative and model-based methods. Then I will generalize and show how we can solve optimal control problems of a discrete and continuous time system with reinforcement learning, and then provide, again, policy and value iteration frameworks to solve these discrete and continuous time systems. Then I will talk about what is called value function approximation, and then I will talk about Q-learning, which are action-dependent functions. And then finally, I will conclude and talk about future work. So let's say reinforcement learning nowadays has been in the center of many fields. One of them is, of course, control. So learning from the control side has been around for many years, including the intelligent people who worked on intelligent control, where they used neural networks for approximation or in feedback loop. Of course, people also, they have used reinforcement learning back in the days. Also, people work on adaptive control, actor-critic structures, etc., etc. But of course, when you bring this together with optimization, so then you can solve game-theoretic problems, you can solve optimal control problems, H-infinity control problems, dynamic programming problems, etc., etc. And the idea that brings these two things together, these two bubbles, is called approximate dynamic programming. As you all know, dynamic programming suffers from the cost of dimensionality, and everything has to be solved backwards in time. Approximate dynamic programming solves everything forward in time, is the basis for reinforcement learning, and solves the cost of dimensionality. Of course, as controls people, we're also interested in what is called distributed control. So we want to make everything in a more distributed way. Okay, so this was the little how everything interacts in this bubble. So again, we need ideas from learning itself for optimization and from distributed control to design efficient learning-based systems. So let's describe what is an optimal control problem and why it is important. So optimality in control systems can appear in different ways. First, whenever you want to minimize something, you want to minimize, for example, fuel, energy, minimize time where a missile can intercept another missile, or in a pursuit evasion game where you want to pursue something and then you want to pursue it in a minimum time. So all these things, they are the basis for optimization. Of course, if we go to application side, aerospace design problems, for example, interplanetary trajectory design, is a very important optimal control problem. In biology, how you can give the optimal dose of drugs. In computer science, cybersecurity defense is also an optimization problem where you can solve it as a mini-max optimization problem, where you are the good player and the bad player, and you have to have the best answer towards the worst case attack that can happen. Also in economic, we have strategic decision on investment and things like that. Of course, in controls, we are more pessimists than optimists, because in economics, they want to maximize things. In control, we want to minimize things. So, because we want to minimize the fuel, the energy, the time, etc., etc. So, of course, as you can see here, optimal decision-making is found in almost all sciences. So, systems, they can evolve in discrete or continuous time, and then their action and state can also be in discrete or continuous time. So for example, if you have a continuous time system, so then your performance will be given by this j, where your u is the variable that you can put into the system, and you want to optimize it such as this cost here is minimum, and this Rx, u, t can be either the fuel, energy, or time, or a combination of those. And then we want to have everything constrained by the trajectory of the system, so we have an equality constraint which is given by this physics of the system. So this is the continuous time optimization problem. Of course, we also have a discrete time optimization problem, so where instead of having integrals and ordinary differential equations, you have differences and summations. Everything else is the same. Okay? So, again, in reinforcement learning, this part over here and this part over here is called reward or cost. So people in learning call the reward, people in control call it cost. So people here in control call this F, and F, they call it system. People in learning, they call it environment. So again, I will use these terms interchangeably. Okay, so let's talk about first about optimal control for Markov decision problems. So Markov decision problems are sequential optimal control problems. Of course, they have been developed first for discrete time and state systems. So let's say I give you a model which is a Markov decision process, and then this has the state space X, this has the control state U, this has the transition dynamic which predicts the next state. So again, given the U and given that I am in state X, what is the probability of being in state X prime? And then this is the reward function which predicts the next immediate reward. So the objective now for a Markov decision process can be given in a similar framework where you have seen before for the discrete time systems. So here what you can see is that this R is my reward, okay? And then we can call it anything, and it's any function of xk, uk, and xk plus 1. The gamma that you see there is a discount factor, okay? So this actually penalizes how far and how short-sighted I am, okay? So in other words, if I care about my immediate rewards or my future rewards. Okay, so two very important books in reinforcement learning are, of course, the book by Sutton and Barto and the book by Dimitri Berchekas. So what we want to do in optimal control for Markov decision processes, we want to design feedback policies. So, of course, this feedback policy takes my state and my action and maps it to integral between a 0 or 1. So in other words, it's a feedback as a distribution over actions. And of course, this is also stationary in time for a Markov decision process. So again, we can define that as the function of x, which is the probability that I am in x and I pick control u. Okay, so this is again my policy. Okay, so let's see actually what we want to do. Our ultimate goal is to find this pi, x, u, that minimizes the cost that you saw before. So in order for me to solve this cost that you saw before, I have to define what is called as a value of the policy. So in other words, I put a policy. What is the value by putting this policy? Okay, and this is given by this guy over here, and this is at instant k. My state is k. Okay, and then I give you my reward can be evaluated from k to k plus t, and then I can find this is called the value of the policy. Okay, so again, what is that? Is the cost starting from state x using policy pi x, u. Now, if I want to find this optimal policy, what I will do, I will optimize this value of the policy, and then I can write it like that. Okay, so again, this optimal policy is the argmean of vk pi x. Okay, so it's whatever the policy that optimizes this value, it's called optimal policy. And then if I take my optimal policy that I found from here and I put it back to my value, then I will find what is called optimal value. Okay? Note that the optimal value is a function only of x because I have already substituted my optimal policy. Okay, so now what I want to do is in MDPS and in general in reinforcement learning, I want to do recursive forms of the cost. Okay, so what I want to do is I want to separate the first term, which is rk, and I want to write that with respect to k plus 1 up to k plus t. Why? Because I want to bring it to what is called Bellman's equation, where you can say that as long as in one policy, whatever I pick, it will be based on an optimal policy. Okay, so if of course you want to use transition matrix dynamics, so all my costs that you see here can be defined as you see over here, given the transition, the probability transition dynamics and the rewards. Okay, everything else is the same. Okay, so this is now using your transition matrix dynamics. This is what is called a backwards recursion form. Okay, so what I have done, I have isolated in two terms, my kth term and my future terms. Because note here, I start from k, I separate the k term, and here I have everything else, which is, you can call it as a tail. And here I rewrote that with respect to the transition matrix dynamics, and hence I have this backwards recursion form, okay? Where pi are the policies, this is the probability, this is the reward, and this is the future cost. Okay, so now, under ergodicity assumptions, the system has stationary policies. So let's say now that instead of going to a finite horizon, I go to infinite horizon. So then what I can do, my backward recursion that you saw before becomes the Bellman equation. Okay, so this is again, this is the future, and this is where I am right now. Okay, so you can see that the same term appears on both sides. So this is a system of linear equations which has the same number of equations with the same number of states. And then, if of course you go back to what you saw before and put your optimal policy inside your value, then you will find what is called Hamilton-Jacobi-Bellman equation. Okay, what I substituted here is I put the star here, okay, and I found the u, which actually is minimizing this term over here, okay, because this is where the u appears, okay, and then I do that for every k. So in other words, at every instant k, I find one vector that minimizes that. This is actually the Bellman's principle of optimality, and this equation is the Hamilton-Jacobi-Bellman equation. So this is, again, this gives you the optimal value, it gives you the optimal policy, but they're very difficult to solve because this is a system of nonlinear equations, okay? All these transition dynamics, all these things, they are mostly unknown in nonlinear equations. So it's very, very difficult to solve. So what happens now if we simplify things? Or we can take directly to control, and instead of having an MDP, we apply it on LQR problem. Okay? So instead of having the MDP that you saw before, the classical MDP, you can think that also this is also somehow an MDP, which is a deterministic with a deterministic linear state transitions. So this goes back to your linear time invariant discrete time system that appears in control, where xk plus 1 is axk plus buk, where your x is your state and u is your control. And this is your infinite horizon quadratic cost, where u is positive semi-definite and r is positive definite. Okay, so if I want to go now and do whatever I did before for the Markov decision processes, I can write this Bellman equation in this way, okay? So Vxk, as you saw from before, is the cost at k plus the tail at k plus 1, okay? Again, if you remember for the Markov decision processes, my optimal, my cost is evaluated as the cost at k plus the future. So if I substitute now Vxk, the classical quadratic on the state, and my u is a feedback, minus k xk, where k, I don't know what it is yet, but you will see eventually it will be the Kalman gain. So, of course, p here, if it is unique, it has to be positive definite. And then, of course, we can make all the assumptions about a square root q. Observable, then my p is unique and positive definite. If I cannot guarantee that a square root q is observable, then p is positive semi-definite. So what this happens is, if I substitute this Vxk and uk inside the Bellman equation, then I will have the linear Lyapunov equation, okay, where k is the Kalman gain, and eventually it can be picked by using the Riccati matrix. Okay, so now let's say actually how can I apply the Bellman equations that you saw before to an LQR problem. So the Hamiltonian of the system is actually the cost, okay, plus the xk plus 1, p, xk plus 1, minus the cost at xk, at k, okay? So if you apply the stationarity conditions, so then I can find my UK, what you can think is my optimal policy. So my policy here becomes this guy over here, okay? So this B transpose PB plus R inverse B transpose PA is what you can see from before here. It's your K matrix, okay? So after now, you find this and you put it back to your Hamiltonian, you will eventually have your Riccati, okay? Or a Hamilton-Jacobi-Bellman equation, which is in a general nonlinear sense, okay? Again, what I did here is I applied the Bellman equation, where you see in this way here, okay? And I applied it, so this is the Bellman equation, okay? And then I applied it to the Hamiltonian. And then based on that, I can find what is my optimal control, my optimal policy, and then if I put this back to the Hamiltonian, then the Hamiltonian is equal to 0. In the nonlinear system, this becomes the Hamilton-Jacobi-Bellman equation, and in the linear system, this is just the Riccati. Okay, so reinforcement learning is a collection of algorithms that will allow us to solve these nonlinear optimal value equations via interaction with an environment. Okay, let's see how we can do that. First, again, I will take the simplified version in an MDP sense. So what I want to do, I want to iterate between two different procedures. So first, from this Bellman equation, okay, I want to find how good my policy was, okay? So in other words, I want to find the cost given the policy. So this is what is called policy evaluation. Then, after I find this one, I want to improve my policy by using greedy optimization. So these are the very famous steps which are called policy evaluation and policy improvement. Again, in the policy evaluation, I check how good is my cost. In the policy improvement, I actually improve my policy, and I do that repeatedly. Okay, so the algorithms that iterate between the two procedures of policy evaluation and policy improvement have been shown to converge under mild conditions for Markov diffusion processes. And of course, for those of you who are interested, actually the analysis is based on Banach's fixed point theorem. In other words, you can find that under what certain condition there is a unique fixed point. This fixed point is the limit of a certain computable sequence, and then I can provide how close I am of the sequence to the fixed point. So iterations that solve these two steps, the policy evaluation, the policy improvement, in the reinforcement learning framework are called policy iteration and value iteration. Let's first talk about the policy iteration. So again, why I want this policy iteration? Because the Hamilton-Jacobi-Bellman equation that appears in most of the control problems with nonlinear systems are intractable. Okay, so what I want to do is, instead of solving these intractable equations, I want to relax them to Lyapunov equations, which are simpler to solve given a predefined policy. And then, of course, I can use approximations of the Hamilton-Jacobi-Bellman equation via iterations of the Bellman equations. And of course, these also require knowledge of the system dynamics. Okay, and also policy iteration requires to start with an initial admissible policy. What does it mean as an initial admissible policy? It means that my policy has to be first stabilizing, okay, and second, it has to give me a finite cost. Okay, so let's see how this will work. Let's first start with the policy iteration for Markov decision processes, which actually is a reinforcement learning mechanism. Okay, I start with an initial admissible feedback control policy I0. Okay, again, an admissible control policy is a policy that produces a finite cost and is stabilizable. Now, I will do the iteration, okay? For every j given pi, I will solve the Bellman equation and I will find how good my policy was. So this is a system of linear equation, and I solve this one for every j. So this is the j. So I solve this equation and I find how good my policy was. Then I update my control policy at the next time instant and I run that recursively. Okay, so again, this is the policy evaluation and this is the policy improvement. The policy iteration is to start with an admissible policy. Okay, so this is interactions with the environment to solve this linear equation at every step, and then at the next step update the policy and do that recursively. So infinite Markov chains with n states, so the policy iteration will converge in less than n steps. Okay, and of course when you have this, as we talked about, the Hamilton-Jacobi-Bellman equation, which is this equation over here, you can transform that to a linear sequence of Bellman equations. Okay? Okay, so now let's talk about what is called value iteration for MDPs. So I start with any feedback policy. Value iteration, I don't really need to start with a stabilizing policy. Then what I do is, as the word says, I do iterations on the value, okay? So this is the policy evaluation, but you see I have here j plus 1 and j, okay? So this is a single equation and not a system. And then update the control policy, which is again a j plus 1, okay? Again, I do iteration on j, here I have j, here I have j plus 1, and then I update my control policy. Okay? Again, what I want you to see here is I want you to see the differences. Okay? So here I have j plus 1. I start with initial admissible policy. Here I have j plus 1. I do iterations on the value. And here I have j plus 1. I start with any feedback policy. Now, what are the differences? Somebody will ask, okay, so if the value iteration doesn't require admissible policy, why I don't do just value iteration? You know, value iteration is slower than policy iteration, okay? Does not solve Bellman equation, it does not require admissible stabilized initial policy, as I said, okay? So of course, every method has its pros and cons, okay? Okay, so now, let's actually go now and see how we can put policy iteration and value iteration that is used in reinforcement learning. How can we use it in control in a famous problem of linear quadratic regulator? Okay, so what I will do, I want to do policy iteration. So I will start with an initial feedback control policy that will be admissible. Okay, so for j, I do the iterations. Okay, so what I will do now, instead of having the general MDPs, I will have these equations here. Okay, so here's my LQR cost, and these are my V's. But note that here I have j plus 1, here I have xk plus 1. Okay, and then if you want to write it with respect to x transpose pjx, which is quadratic, because remember, when we solve the Riccati, your cost is actually quadratic in the state, and then it's multiplied with p, where p as I said, is positive definite and unique if a square root q is observable. So after I substitute this Vj in the left-hand side and the right-hand side, so I will have a recursion, okay, and I can solve for pj plus 1, okay, and then I have this Lyapunov equation, okay? And then after that, what I do, I update the control policy using this law, okay? So mj plus 1 is argmin of what you see on the right-hand side. And then I do that recursively, okay? And then eventually, I will find that this is the Kalman gain, where I have my pj plus 1, okay? So again, I do that recursively, okay? So this is a very famous paper, actually, that has studied that in 1971. Of course, this was not really in terms of reinforcement learning, but it is the basis for reinforcement learning. Now, let's talk about value iteration for discrete time LQR. Start with an initial feedback control policy. Update your cost using one iteration of the Bellman's recursion. Okay, so here as you see, I don't have j plus 1 and j plus 1. I have j plus 1 and j. Okay, so what I will do, I will substitute my Vjx, x transpose Pjx, and I will have Pj on the left hand, Pj plus 1 on the left hand side and Pj on the right hand side. This is not a solution to the Bellman equation though. This is this equation over here, where you have Pj plus 1 and Pj here. And then I want to find this Kj, okay? So how we can find the Kj? I will update the control policy using this equation, okay? And then this equation actually minimizes the right-hand side of this guy over here. Okay, and then eventually I can find my Kalman gain and I can put it back, and I do that iteratively until I converge. Okay, so of course, if I have nonlinear dynamics, okay, so things are becoming tougher and tougher. So here I have a nonlinear f, a nonlinear g, and a u. Okay, so again, what I want to do first, I want to achieve optimal regulation. So let's say that the value function is given by this guy over here, where your gamma is your discount factor, your q is a positive definite, it's a positive definite, and then UK transpose R UK is also analyzes the use, and R is positive definite. Okay, so the first thing that we can do is we want to write the Hamiltonian, right? So the Hamiltonian of this system is given by what you see here, plus the V, the gamma V, minus the Vm. Okay, so this is just the Hamiltonian of the system, nothing too interesting here. Okay, so the optimal policy goes by doing stationarity condition on my Hamiltonian, and it's given by this guy over here. Now, if I want to take this, to find this in a recursive way, and I want to define the Bellman equation, so what I have this guy over here, which again, all these things are the basis for reinforcement learning. I want you to see that everything that has to do with optimal control in Markov decision processes, in LQR, in general nonlinear systems, is the basis for reinforcement learning for control. Okay, because what you want to do in reinforcement learning for control, you want to eventually do optimal control. And then this is your Bellman equation. Okay, here is, and then xk plus 1, v star xk plus 1. This is the cost right now, and this is v star xk, and if you do the minimum of that, this is the actual Bellman equation. Okay, or you can call it Hamilton-Jacobi-Bellman equation. Okay, so now let's actually talk about policy iteration for nonlinear systems. So the policy iteration for nonlinear system actually brings together optimality and adaptation. Let's see how we can do that. So you start with an initial feedback control policy, which is, of course, an admissible policy. Now, given a policy mu, you want to solve for your cost using the Bellman equation. Okay? So now, the Bellman equation is nonlinear, okay? Because your dynamics are nonlinear. So this is the general equation. You update the control policy using your cost that you found before, using your control that you found before, And you do that recursively. Again, in your policy iteration, you have j plus 1, your u is uj plus 1. Now, if I want to do continuous time optimal control problems, things are kind of trickier. So in continuous time control problems, let's say that I want to do optimal regulation. Let's say that this is my value function starting from t to infinity. My Hamiltonian is what you see inside here, plus I adjoin my dynamics, which are fx plus gxu. Okay? So now the optimal policy is given by, so here I forgot my gx. Okay? So my optimal policy is given by doing stationarity condition of the Hamiltonian. And then this is given by this u star x. After I take my u star and I put it back into my Hamiltonian, I will have my Hamilton-Jacobi-Bellman equation in continuous time systems. And of course, reinforcement learning will let us solve this either recursively or by using approximations. Let's see how we can do that. So, policy iteration for continuous time systems. Start with a stabilizing feedback control policy. I give you j, and then what I do, I solve this equation for vj. Okay? Then, after I solve this equation, I update my control. Okay? So this is a very simple linear Lyapunov equation, and this is my control. And I do that recursively by starting with an initial stabilizing policy. Okay? So again, this is very easier than solving this partial differential equation, because this reduces to a just simple linear Lyapunov equation. Okay, and I do that recursively. But how do we solve the Bellman equation, which is this guy over here, during policy evaluation? Let's see. So we have a lot of details about these things, and of course, many people have written papers on that, and we have written papers, but they're shaped towards control only. So we have 2 magazine articles, and we have also a survey that appeared in IEEE Transactions and Neural Networks and Learning Systems. So if you want to learn more, I encourage you to go deeper into these things. So now, again, I don't want this equation here. Again, this equation is a Lyapunov equation. It has lots of problems because it's, again, difficult to solve. What I want to do is I want to solve it approximately. Okay? So this is the idea. Let's see how we can do that. So this is what is called now value function approximation. I want to approximate my value. So instead of having this Lyapunov equation, I can have an algebraic equation with respect to the weights. So now I can approximate my value given Weierstrass higher order approximation theorem. So for example, for every v that you see there, I can represent it with a basis phi of x, a set of weights w, and an approximation error. Of course, since I don't really know this approximation error, I will consider current weights, which are given by this guy over here. Now, if I take my v and substitute it inside my Hamiltonian, okay, so then you remember that I had here dv dx. If I take dv dx, partial derivative of v with respect to x, so then this guy over here becomes w transpose delta phi x. Okay, so this is not 0 anymore because I have put my approximation there. What is here? This is equal to epsilon h, which is the residual. So if I take these w's and find the optimal ones, so then my residual will be 0. So again, if I learn my w, my residual will be 0. This is a key point here. So as I include more layers here, so you can think that if you include more neurons in your value function approximation, this will be 0, and I will compute my optimal cost and my optimal dv. Okay? So, so again, these things, as I increase my number of neurons or my number of bases, according to Weierstrass high order approximation theorem, my E8 will be very, very, very close to 0, and I will approximate my V star and also my dvdx, which is this guy over here. Okay? Okay. So in order for me to now do reinforcement learning or data-driven policy evaluation for discrete time system, I will use trajectory data, okay? And then I will base my tuning laws to tune these guys over here on least squares or recursive least squares, okay? So again, this is just, I rewrote my my Lyapunov equation that appears in the policy iteration. I rewrote it with respect to W's, okay? And here, as you can think, this is the discount factor, okay? So this can be solved by least squares, recursive least squares, gradient descent, anything you can imagine, okay? By gathering data along the trajectories. And again, you can update the control policy by using again these W's here. So instead of solving this problem that you saw before in a linear Lyapunov equation, here you have an algebraic equation with respect to the weights, okay? So iterations between these things, in a policy iteration sense, will learn the W's, and this is actually the base of value function approximation in reinforcement learning. So, of course, in continuous time systems, the things are not that easy. So we have worked on many papers, actually along with many other people, but I think we are the first people that we solved this continuous time infinite horizon optimal control problem by using reinforcement learning. So what we did is, remember, my Hamiltonian, due to approximation errors, has an error E. So what I do, I define a new performance, which is 1/2 E squared, and then I want to use gradient descent on that. A normalized gradient descent, because the normalization in the gradient descent will actually help us in developing Lyapunov closed loop Lyapunov stability. Okay, and of course here this sigma has to be persistently exciting. Okay, so excitation now in optimal control and learning optimal control solution by using reinforcement learning, you can think is about the problem that you have in classical reinforcement learning on exploration versus exploitation. So in other words, what I want here, I want my sigma to be rich enough signal. So for example, if I have a linear system and the order of my linear system is n, I want to excite the system by adding n multiplied with n plus 1 over 2 different frequencies. Okay? In the nonlinear systems, you know, excitation, I will call it as magic because there is no clear way to find this excitation. And of course, as you can see, excitation has to be guaranteed for the future. So up to now, people, they have been working to guarantee this into the future, but also there is in learning, there is what is called experience replay, where whatever you have learned before, you store them in a buffer, and then you use that to guarantee that your system is persistently exciting. And of course, everything we do, we provide proofs and we converge to the optimal solution, given some residual sets. Okay? So now, this is the basis for synchronous reinforcement learning. Remember, what we have done before, the policy evaluation and the policy improvement of the policy iteration and the value iteration, they have to be run separately, and we do that iteratively. So what we have developed through the years, we have developed what is called synchronous reinforcement learning, where you do both steps simultaneously. So this is the idea of optimal adaptive control algorithms, which is actually by bringing optimal control and adaptive control together, what you have synchronous reinforcement learning. And we use completely online data. We don't require any pre-training, and then we use gradient descent-based tuning laws. So this is actually based on an actor-critic structure, where your critic approximates how good your control is, and your actor approximates your optimal control. But the tuning laws for these two things, they will be updated based on the gradient descent-based tuning laws. Okay, so an actor approximator has this form, okay, where WU's are weights, phi U are bases, and then phi U, you can be of this basis, okay? And then the critic, as you saw before, is actually the approximations of the value, okay? And then don't worry too much about this, but I want you to know that by plugging what you saw here, this guy over here, by plugging this W dot, and by plugging this without any pre-training, you will learn the solution of the optimal control problem in real time, okay, without any pre-training and without solving complicated equations. So this equation requires the model. We have developed through the years equations that don't require the model. And this is given here, where instead of writing with respect to the Hamiltonian, we use it in, we write it with respect to an integral form of the Hamiltonian, and we call this as integral reinforcement learning. So this integral reinforcement learning doesn't require the drift dynamics. So in other words, I can solve my optimal control problem forward in time online without requiring fx, or I can solve my Riccati equation forward in time without requiring matrix A. So this is actually, as I said, is a model-free version of the Hamilton-Jacobi equation, or some people, they call it integral Bellman equation, okay? So you can think that this is just an integral form of the Bellman equation. And this t is an arbitrary time interval. Of course, if this is very, very small, of course, you get more data. If this is large, you get less data, okay? And of course, if I use approximation structures for V, in other words, if I use the critic, then I can approximate this guy over here, and I can design my tuning laws for WC by using gradient descent tuning laws. Okay, and of course, again, I can just optimize my optimal control policy by using this actor. Okay, so again, what I want to do, I want to find the critic tuning law, which is given in this guy, okay? The details can be appear in the paper. In the papers. So this guy doesn't have any dynamics here, okay? The actor has this form, okay? The only caveat here is that my G appears, but my F never appears. So what I do, if I plug this WC dot and WU dot in my system, real time, by measuring the trajectory, I will eventually converge to the solution of the Hamilton-Jacobi-Bellman equation without knowing f of x, okay? I will learn the solution of the optimal control problem in real time by using an actor-critic structure. Okay, so this is actually the actor-critic structure. Okay, so this is my system. My actor implements the control policy, and the critic evaluates the control policy, how good they're doing. So you can think that the system will give you a reward. This reward will be passed from the critic, and based on this reward from the critic, you will update your actor. Okay, so again, the intelligent agents of the future will need to learn from mistakes, improve over time, interact with each other in an intelligent way, operate under unforeseen circumstances. They're impossible to pre-program behaviors, and then of course, so anytime that you train something on something that you haven't seen will not work if you put it into the field. Okay, so as controls people, we have this beauty of the feedback. Okay, this beauty of the feedback will let us provide stability, robustness, and convergence guarantees that when you do pre-training and then when you go to environments that you haven't seen, you cannot guarantee. Okay? Okay, so now that we talked about the model-based frameworks, we can talk about Q-learning. So Q-learning was developed by Watkins, and it was developed primarily for MDPs. So how we apply the Q-learning that Watkins developed, how we can apply it to discrete time optimal control systems. It's very interesting. It has a very interesting procedure. And in the continuous time system, it has even more interesting procedure. Let's see actually how we can do that. So the Q-learning has the beauty that doesn't require the transition matrix, the transition dynamics. In other words, it's completely model-free. Why? Because it's not based on just the state, but it's based on the pair of state and action. So the idea of Q-learning is that given any non-optimal action, you can converge to the optimal action. Okay? So let's see. So instead of having this value function, which is the Bellman equation here, you have a Q function. So instead of having a function of the state, you have an action-dependent function. Okay? So take arbitrary action for a single step and continue with given policy. This is actually what is called a Q function. Okay, so of course, the recursive equation, I can substitute this guy here with a Q function as well, and I can have a recursive equation for Q. Okay, so this equation here doesn't require any transition dynamics, any information of x, fx, gx, any information on a, b, etc., etc. Okay, so again, instead of writing with respect to, of course, this is the Bellman equation, and it will be given the same cost exactly. So for example, every time I minimize my Q star with respect to U, I will take the V star. And then my mu, my policy mu, won't be based on H or V, but it will be based on the Q function, okay? Because it's completely model free. Let's see actually what we can do here. Let's actually do a policy iteration algorithm for the Q function. I will start with an initial stabilizing feedback control policy, mu 0. Now, for every j, I will give you an action, and then I will do iterations on the Q function in a similar way that I did iterations on the value function. And then I update my mu. So here again, this is the Q, and here is the mu, okay? And then does not require knowledge of the system dynamics, okay? Now, the Q learning can be also implemented in episode, which is called episodic Q learning. So given initial state of episode x0, you define the number of steps in episode n, and then at each step, you choose the greedy action uk. You observe the resulting state xk plus 1, and then you define the Q function, okay, which is the update law. So this is the update law, okay, and then you can think that these differences will tell you how close you are, okay? So you repeat this episode until convergence of the Q function that you see here. Now, the convergence of learning schemes are investigated in terms of stability and convergence. So what does it mean by stability? Stability means that intermediate policies do not lead to instabilities, and convergence means that the optimal policy is found eventually. Most of the proofs are based on contraction mappings, and you design learning algorithms where the approximations come closer at each iteration in this sense, okay? So you develop a threshold where your policy iteration and your value iteration will converge, and if two consecutive value functions are close to each other, either value functions or Q functions, so then I terminate my algorithm, okay? And then of course you can prove those things by using contraction mappings, monotonicity proofs, etc., etc. Now let's bring the connection back to the LQR problem, which is a very important problem in control. So in LQR, the value is quadratic, okay? Now, the Q function is not only quadratic in the state, but it's also quadratic in the U, okay? So now, instead of having the value function, which is only the state, I have xk and uk, okay? So eventually, I have this pair, xk, uk, and I have something here, a Q matrix, okay? This, eventually, that's what I want to learn, or H, or whatever you want to call it, okay? So this matrix here is the unknown matrix. So I can do now, I can learn this by using value function. I can do any policy evaluation, any policy improvement, but these are applied to the Q function, okay? And of course, I calculate the optimal control based on the Q function, and it will give me something which is unknown here, okay? So what I want to do is if I find this H matrix here, I will find the optimal control eventually. So this is a very famous paper which is called Greedy Adaptive Greedies for LQR Problems with Convergence Proofs. This is by Landelius and Nugent. Okay, so for continuous time though, it hasn't been developed yet. Why? Because the Hamiltonian in the continuous time has the dynamics, but the Hamiltonian in the discrete time doesn't have the dynamics. So what we have done is for continuous time LQR problems, we will define what is called as advantage function, which QXU equals V star plus the Hamiltonian with dV star. So this is the action-dependent pre-Hamiltonian function. And then the optimal Q function will satisfy this one. And guess what? This is what you want, because your Q with the star inside has to be the V star. So we published a paper, which again uses this XU. We published a paper in System and Control Letters, which is a Q learning framework for continuous time linear quadratic regulator systems. And we provide again tuning laws for the critic and the actor, where if you can plug them into the system, you will solve the Riccati equation online without requiring A and B. Okay, so to conclude my talk and suggest some open topics, so I want you to see that reinforcement learning is one of the most active research areas in the computer science and the control communities. What we talked today, we proposed methods that apply the same principles to different system abstractions, including MDPS, discrete and continuous time systems. We did approximate dynamic programming that maps to eventual Lyapunov equation problems. We provided policy iteration methods with value function approximations, and then we saw least squares and gradient-based algorithms to evaluate these policies. And then we have also solved some recent work in reinforcement learning for continuous time systems. Open topics. We need to investigate the effect of the disturbances and malicious inputs from the environment. We want to develop robust methods that guarantee convergence while safety constraints are satisfied. We want to analyze sensor behavior and construct output feedback policies. And we want to investigate the use of deep reinforcement learning control theoretic models. And then with that, I would like to thank my advisor, Frank Lewis, my postdoc advisor, Joao Espania, and Aris for their help and their inspiration during the years. And of course, I would like to thank our sponsors. And also, I want you to pay attention also to, if you are interested in learning more about that, we have published 2 books, and we have another handbook with our editors, which is called Handbook of Reinforcement Learning and Control. And with that, I would like to thank you, and I will be happy to answer any questions. Send me an email or anything you want. Thank you very much.